Good morning, class. We're looking at chapter 4, application of derivatives. Here's section 4.2, how derivatives affect the shape of a graph. So we covered maximum and minimum values, and now how derivatives affect the shape of a graph, starting with differentiation formulas. By definition, f prime of x is limit of f of x plus h minus f of x over h as h approaches 0. Here's two ways to define a number e. Differentiation formulas from the power rule to trigonometric functions. If you have a constant, you can take the derivative and multiply it by constant. If you have a bunch of terms, basically this indicates to differentiate term by term, product and quotient rules, composite function giving us the chain rule, the power rule, and the extended power rule as a result of the chain rule. Every exponential results in the same answer exponential. In these two cases, by the chain rule times k here times g prime here. In this case, by logarithmic properties times ln b. In this case, times ln b as well as f prime by the chain. Logarithmic differentiation, you flip it over and you multiply by the derivative of the argument of log. And now, if you have point P and Q on a curve, as we move from P to Q, we create a run delta x, which is dx or bp, and we create a rise. They create the rise along the curve versus the rise along the tangent line. Along the curve, we call it delta y, this distance, which is f of x plus delta x minus f of x. Along the tangent line, we call it dy, which is f prime of x dx, and that can approximate delta y. Also, linearization means find the equation of a tangent. Local extrema. Local or relative extreme value is the plural of the Latin extremum. Local minimum occurs at the point C in an open interval of a to b in the domain if f of c is less than or equal to f of x for all x values in the open interval. Local maximum occurs at the point C in an open interval of a to b if the in the domain if f of c is larger than or equal to f of x for all x values in the open interval. In other words, peaks and valleys, everybody. Local mean, local max, local mean, local max. What about absolute, also known as global extreme values? Absolute minimum occurs at the point C if f of c is less than or equal to f of x for all, and that's the key word, all x values versus some open interval. In the domain, absolute maximum occurs at the point C if f of c is greater than or equal to f of x for all x values in the domain. So, as you can see, again, peaks and valleys are local extrema. Local mean, local max, local mean, local max, local mean, local max, but this local minimum is also absolute minimum, this local maximum is also absolute maximum. In order to find the critical point, number one, find f prime. Number two, look for where f prime is 0. And number three, where f prime does not exist. Finally, the extreme value theorem, also known as the closed interval theorem method, indicates if f of x is a continuous function and the closed interval is given, we want to find all CPs and evaluate the function at the endpoints as well as the CPs. Absolute max, the largest value, absolute mean is the smallest value. So this is the synopsis of what we covered. And now 4.2 summary, how derivatives affect the shape of a graph. Here's the summary. A function is increasing where f prime is positive. A function is decreasing where f prime is negative. So as we look at these two graphs, it seems that it's similar to a line with a positive slope here. F prime is increasing, similar to a function where f prime is when a line has a negative slope. A critical point C of a function is a point where f prime is either 0 or doesn't exist. Was discussed before. A relative maximum or relative minimum is a critical point at the top or bottom of an interval of a graph, peaks and valleys. A function is concave up where f double prime is positive means f prime is increasing. Concave up, it can hold water, and a function is concave down where f double prime is negative or f prime is decreasing. And in other words, if you look at that one, can't hold water. That's what we discussed in algebra calculus, pre-calculus. An inflection point C is the point where concavity changes. Inflection point occurs where f double prime is either 0 or does not exist, as you can see in this graph. Concave down, concave up. Point of inflection is where it changes from one format to the next. Now, as we continue with that concept, concave up means the graph of f of x lies above all its tangent lines on an open interval. Concave down, the graph of f of x lies below all of its tangent lines on an open interval. So if you look at this one, it's above the tangent line in these two cases, whereas in these two cases, the graph of the function is below the tangent lines. And if we add and get more than one, what happens? Take a look. Over here, we have two tangent lines. When it's concave up, slope of tangent lines increase. Take a look. If you draw a tangent line, you can clearly see that both of them have positive slope, but this is steeper, therefore it is increasing, it's getting larger. Both of these negative slope, but this is steeper, so this is larger than this one. Therefore, f double prime is positive, f prime is increasing. This is the other way around, concave down. Slopes of tangent lines decrease. Notice negative, it's more negative here. Positive, but it's less positive here. So f double prime is negative, f prime is decreasing. Finally, a point P on a continuous curve f of x is an inflection point, is f of x changes concavity. Take a look. Concave down to concave up. This is the point of inflection. Concave up to concave down, point of inflection. So that's pretty straightforward. And now, how do we graph functions? In addition to pre-calculus step, and I want to discuss that one, we should have some information about basic essential functions. We should know how to find intercepts. Okay, then I'm going to remind you of behavior near an x-intercept and the endpoints, if you will. Okay, we will discuss that. And of course, as I mentioned, how the graph looks like and if need be transformation. Aside from that, now we are going to find relative maximum and minimum and intervals where the function increases and decreases. That means set f prime equal to 0, solve for x, and then do the sign graph, which means number line and test values in between for critical numbers. Number 2, we find inflection points. That means set f double prime equal to 0 and solve for x. Make a sign graph, find possible inflection points IP and where the function is concave up or concave down. And finally, put all this information together and sketch the graph. Extreme values of a function are created when the function changes from increasing to decreasing or from decreasing to increasing. In other words, as you look here, first it's increasing, then it's decreasing. And obviously, at top here, we have an extreme value. More importantly, more specifically, we have a local max, decreasing, increasing, extreme value, local mean. Look at this one, decreasing, increasing, local mean, increasing, decreasing, local max. Okay. Here, increasing, decreasing, increasing, decreasing, and we have extreme values at peaks and valleys. Therefore, a function is increasing where f prime is positive and decreasing where f prime is negative. We can look at the proof using the mean value theorem. This theorem is discussed in regular calculus course. I want to quickly mention that you're not responsible for it. If f is a continuous function in the closed interval of a to b, CT is short for continuous, and if f is differentiable, DIFF, short for differentiable on the open interval of a to b, then f prime of c must be equal to f of b minus f of a over b minus a. Meaning, here's point A, here's point B. Normally we choose B to be on the right side. And this point has coordinates a comma f of a. This point has coordinates b f of b. Look at this point. And if you connect the two, it gives you a secant line. And you can calculate the slope. What is the slope? That's exactly what we have here. Because the function is continuous in the closed interval and differentiable in the open interval. Differentiable means nice and smooth in essence. Therefore, there must be a point where the tangent line is parallel. Some point C where the tangent line is parallel. And also, this is equivalent to that class if I do the cross product here. Okay, I get f of b minus f of a is equal to f prime of c times b minus a, meaning these two are equivalent. So we know the meaning of increasing. The short way to write it, as x gets larger, so does y. That's the meaning of increasing. In other words, as I go from left to right, so obviously b is larger than a. What about the y coordinate f of b? If that one is larger, that makes it increasing. So let b be larger than a, meaning choose b to be on the right side. If f prime is positive, then this must be positive. So take a look. We are saying that b is larger than a. That means b minus a is positive. And if this is positive, then the numerator must be positive also. That makes f of b larger than f of a. And that's the precise definition of an increasing, in case anybody is interested in that. So what is the first derivative test? We have a function y, but then we differentiate, we get y prime or f prime, where it's positive. The curve is falling first, is rising first, my apologies. It's increasing. When it's negative, it's falling, and therefore it creates a local extremum, which is a local max. It creates a peak, local max. On the other hand, if it is decreasing first, that means falling, and then increasing, that means rising. Again, we have a local extremum, but this time is a local mean. And that's it. So where y prime or f prime is 0 or does not exist, those are possible local maximum or minimum. So how do we find them? Use the sign graph. Concavity test, what is that? We take the second derivative. If it's positive, the curve is concave up, looking like that. If it's negative, the curve is concave down, looking like that. And where it's 0 does not exist, those are possible location of inflection points. So we have to go through the sign graph, and if we notice there is a change, either from concave down to concave up or vice versa, that becomes the point of inflection. So a function is concave up where f double prime is positive, that means f prime is increasing, and a function is concave down where f double prime is negative or f prime is decreasing. Methodology, we must use sign graph for this test. We also have something called second derivative test. This is a wonderful test for applications. We don't want to use it for graphs. I will show you for the example, but the reason we don't, because it gives you half of the information of the first derivative test. So what is the process? You find f double prime and then you evaluate f double prime at critical points, what made f prime 0 or does not exist. It is either positive or negative. If it's negative, graph is concave down. When it looks like that, what is this? Local max. On the other hand, if it happened to be positive, it's concave up, looking like that, then it's a local minimum. As I mentioned, a couple of things from pre-calculus, college algebra. One of them is the end behavior of a function. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. In other words, f of x is a sub n x to the power of n all the way to a sub 0. The end behavior means eventually the graph will look like the leading term, a sub n, x to the power of n. So everything depends on the leading term, the degree, and whether a sub n, the leading coefficient, is positive or negative. So if you have even power, if a sub n is positive, it looks like f of x equals x squared. If it's negative, it looks like f of x equals minus x squared, which means either the first and second quadrant or the third and the fourth quadrant. In other words, in this case, x and y, both of them go to positive or negative infinity. Y goes to infinity. In this case, both of them go to negative or positive infinity. Y will go to negative infinity. If you're dealing with odd power, and if a sub n is positive, it looks like y equals x cubed, or f of x equals x cubed. If it's negative, looks like minus x cubed, which means in this case, x goes to negative infinity, so does y. Remember, f of x is y. X goes to infinity, so does y. If x goes to negative infinity, in this case, of x goes to positive infinity. If it goes to infinity, goes to negative infinity. That is the end behavior. Also, we have behavior near 0, which depends on the multiplicity m. When we have x minus c to the power of m, m is called the multiplicity. If m is odd, f crosses the x-axis at c0. If it's even, does not cross the x-axis at c0. So these two are odd, they cross. In this case, they don't. Also, the higher the multiplicity, like this one, the flatter the curve is at the 0, the sum of the multiplicities is the degree of the polynomial function. A lot of information here from previous courses, okay? I hope the synopsis of that helps. And if you need more resources, you can let me know. By the way, if you need more resources, you can go to my YouTube channel. Professor Oro has all types of, college algebra, pre-calculus, you name it. All right. Sketch the graph of y equals x cubed minus 3x squared plus 4. And here's the factored form for the sake of actually intercept. So first and foremost, what I'm going to do, I'm going to graph this using prior knowledge of mathematics, starting with the intercepts. This is at -1, 0. This is at 2, 0. And if I replace the x with 0, it's easier to go with here, 0, 4. I'm assuming nobody has any problem finding intercepts. This doesn't have to be to scale, class, but just to give you an idea. We have -1, 0 here, 2, 0 here, 0, 4 here. And when I look at this one, looks like what? X cubed, the first and the second quadrant. Also, when I look at this one, that means multiplicity 2. This has multiplicity 2. So what it means is that it can't cross that. That's why we put a double arrow. And so to graph this, As you bring it down to this point, it can't cross. It has to go back up. And then how far it goes, we may not know, but it comes back down here. So what happens, we don't know what is the maximum. In other words, it may be like this. Maybe like this. So we don't have this, but we'll find it through using calculus. And that's the difference, okay, class? But practically you have the graph and that's fine. And if need be, you can pick up a couple more points, just put a few more points into the original function, graph it, you're done. But we are going to go with finding relative extrema. So we're going to start with y prime or f prime of x, and I'm going to erase my work because we are going to work on this with more details. 3x squared minus 6x. I'm assuming nobody has any problem with differentiation. Since we want to set this equal to 0, we are going to factor the 3x out, and x becomes either 0 or 2. We go with the number line from negative to positive infinity. We put these two numbers in order from smallest to larger. So we get 0 here, f prime is 0, 2 f prime 0. Please understand, we have x here, and the function we want, in this case, we don't want f of x, we want f prime of x. We do the number line on f prime to get to the first derivative test. And f prime is 0 at 0, and it's 0 at 2. Now, we have 0 and 2, so we have 1, 2, 3 different regions, 3 different subintervals. We pick up what we call test points. So I'm going to call it TP, short for test points. So over here, between 0 and 2, I pick 1, over here 3, over here -1. However, you really don't have to test all of them, because let's go back to y prime. It has degree 2 and it has 2 answers. If you look at each case here, has exponent 1, has an odd exponent. They have to alternate. So if you go with 1 and check it out, okay, if I put the 1 here, it's easier probably to put it here, or I don't know, the factored format, your choice. 3 minus 6 becomes -3. So I'm not interested in the number. I just want the sign. If it's negative here, these two must be positive. Okay, so y prime of -1. Now, if you want to test everything, and you don't have to, as I mentioned, this is good enough. You do one of them. But from -1, if you plug in 3 times -1 quantity squared minus 6 minus 1 is +9, because this is +6, everybody, okay? This is. Okay, so this is 3 plus 6. And so this is 9. We plug in 1, so it's positive. You plug in 1, 3 times 1 squared minus 6 times 1 is -3. This one I had it done for you, it's negative. And if you plug in 3 also, 3 squared is 9 times 3, 27 minus 18 is 9, is positive. And there you have it. I'm going to erase my work, everybody, and I'm going to throw in arrows for positive arrow up, for negative arrow down, because it makes it easier to see. Arrow up and down, local max at x equals 0. Arrow down and up, local mean at x equals 2. Okay, now 0, since we already have the pair, because you have to put it back into original function, so the y-intercept is also a local max. Local mean, we have to put the 2 in the original function, and it happened to be 2, 0, so we don't have to do much of work. local minimum is equal to 0 at 2 or true 0. Now, the function is increasing here and decreasing here. So you're going to say the function is increasing from negative infinity to 0, union, 2 to infinity, and it's decreasing from 0 to 2. So as you can see, the first derivative test gives us a lot of information, everybody. We are going to continue. Now, first, I'm going to write the function. I'm going to write y prime. I'm going to write the critical points. This is what I got from the previous page. And then I'm going to remind you, I'm going to do the second derivative test. You don't need it for a graph. Don't do it. I'm just showing you what it does. If double prime is positive, concave up means relative minimum. If it's negative, concave down, relative maximum. So find y double prime first, which is 6x minus 6. And now evaluate those. If I plug in 0, I get negative 6. So negative means concave down means relative max, looking like that, right? So it gives us the same information as before. And if you plug in 2, 6 times 2 minus 6 is positive. And when it's positive, it means concave up, looking like this, and that should be a local minimum. But it doesn't give us intervals of increasing, decreasing. That's why we don't do that. I'm just showing you the limitation of that. So what do? We are looking for the inflection point. So the next step is to find the inflection point. We have the y, we have the y prime. We have to find y double prime. We already did that, so I'm not going to do it again. Set it equal to 0. X becomes 1. A number line, and reminding you f double prime negative means concave down, positive means concave up. And you do a number line because x equals 1 is a possible IP or an inflection point. We go from negative infinity to infinity for x. But this time we put f double prime. We are doing a sine graph on that. At 1, it's 0. And basically you go with the test point. Obviously, the easiest point for the left side is 0, for the right side is 2. And you put that into y double prime, everybody, just to see if it's negative or positive. So you plug in 0, you plug in 2. If you plug in 0, you get negative 6. And it's negative here. And if you plug in 2, you get positive 6. And it's positive here. So basically, it means if it's negative, concave down here from negative infinity to 1. If it's positive, concave up from 1 to infinity. And because of the change, number 1 is the point of inflection. But what is the y coordinate? You have to put it back into the original function, everybody. So it's easier here. If I put the 1 here, I get 2. And if I put 1 here, I get negative 1. Squared is positive 1, so I get 2. Therefore, IP at x equals 1 because concavity changes precisely at 1, 2. All right. So now we are ready to graph. So to graph this, everybody, I'm going to just rewrite everything we found. Here's the function. Here's y prime. Here's y double prime. Here's the intercepts. Here's increasing, decreasing. Here's concave down, concave up. And I'm going to put everything in summary because it makes it easier that way to graph it. So everything that we have here, I'm going to start from here. And of course, I know the end behavior, right? The first and the third quadrant. So starting with this negative 1, 0 goes here. And by the way, an extra point, if you plug in 3 into this one, you get 4. 3 minus 2 is 1, square it, and you get 3 comma 4. So here's minus 1, 0. Here's 0, 4. And 0, 4 happened to be a maximum, so we draw this. 1, 2, 2, 0, and that's the minimum, so we draw a double-sided arrow. And you really don't need the extra point because you know the end behavior, but just in case 3 comma 4, and here's the graph. And that has everything you want, all your intercepts, increasing, decreasing, increasing, concave down, concave up, point of inflection. So detailed solution is there. We're going to graph this function again using pre-calculus. And to do so, I am going to find all the zeros by setting this equal to 0. To find all the zeros, I'm going to factor either the x squared out or 1/2 x squared. Makes no difference. So this gives me 0, x equals 0. And this gives me x squared equals 2, and x is plus minus square root of 2. So I have the following zeros. And square root of 2 is roughly 1.4, 1.41. And when I look at the leading term, because it's half of x to the power of 4, the degree is even, and 1/2 is positive, it looks like y equals x squared. In other words, I know here's my end behavior, and I'm going to put my zeros, and I'm in good shape. So let's see. We have 0, 0. Square root of 2 is about 1.4, so somewhere here, and negative somewhere here. And if you have the end behavior, if you need be, you can pick up more points. However, what I want to add is this. You see this one? That means the multiplicity is 2. That means this can't cross that. So when you start from the first quadrant and you hit the first, it's called the x-intercept or the root, or the 0 of the function, it crosses, it hits at some point, comes back up, but it can't cross 0, 0, has to come back down and back up again. And also what helps is that if you plug in minus x, you get f of x, and that means it's an even function. And that means the right side and the left side are the same because it must be symmetric with respect to the y-axis. So having said that, we are done using pre-calculus, and it looks pretty good, but we are going to add calculus to make it more precise, everybody. So let's go with calculus. All right, so the first thing is to find CPs, and therefore we are looking for the first derivative test and f prime of x. 1/2 times 4 is 2x cubed minus 2x equals 0. You can factor the 2x, and you get x squared minus 1. And x squared minus 1 is x plus 1x minus 1. So if you set that equal to 0, either x is 0 or -1 or +1. We have 3 answers. So we go with the number line. It goes from negative to positive infinity, x. Number line is for f prime of x. At -1, f prime is 0. At 0 is 0. At 1 is 0. So we pick up test points. Obviously, here, -2, -1/2, let's say +1/2, +2. But You really don't have to test all of it. Plus, f prime has degree 3 and has 3 solutions, or you might say this one has exponent that each one has exponent that is odd. When the exponent is odd, they will alternate in different subintervals. If it's even, they don't. So all you have to pick one of them and evaluate. If you plug in 2 into this one, you get 2 times 2 cubed, which is 8, becomes 16, minus 2 times 2, which is 4. Their difference is 12. We don't care about the number. We just want the sign. The sign is positive here. It will alternate negative, positive, negative. Okay. I'm going to erase my work. And so I'm going to throw in the arrows. Arrow down, decreasing, arrow up, increasing. So this is a local mean. Up and down, local max. Down and up, local mean. So 0, I don't have to do the evaluation. It's been already done for me, 0, 0. So 0, so local max is equal to the y coordinate, which is 0 at 0, 0. So I'm going to find local mean. That means I'm going to put negative 1 and 1 into the original function. And because the original function is an even function, positive and negative results in the same thing. So as you can see, this is 1 and therefore 1/2. This is 1, therefore minus 1, and it's negative 1/2. So local minimum is equal to negative 1/2 at x equals plus minus 1. That means the following two pairs, everybody. As I mentioned, 0, 0. Now, negative means decreasing, negative means decreasing. So it's decreasing from negative infinity to negative 1, union 0 to 1, and it's increasing otherwise from negative 1 to 0, union 1 to infinity. So we have the function, a quick recap. We find f prime, the sign graph gives us local extrema, intervals of increasing, decreasing. We want to go for the inflection point. So I'm going to continue again. This is the function. This is f prime. This is the information we found in the previous page. Now I have to go with f double prime of x, which is 6x squared minus 2. And because I want to do the sign graph on that, I'm going to set it equal to 0. Therefore, I'm going to factor the 2 out. So 3x squared minus 1 is 0. That means 3x squared equals 1. X squared equals 1/3. And x becomes plus minus 1 over square root of 3. Now you plug in to the original function to evaluate it. Okay, but before you do that, are they inflection points? We have to do the sign graph first. So let's do the sign graph. So possible inflection points are negative 1 over square root of 3 as well as positive 1 over square root of 3 over 3, positive 1 over square root of 3. So the number line x goes from negative to positive infinity. F double prime, because we're working on f double prime, is 0 here and here. And now we need to test point, which means over in between, one of them is negative, one of them is positive. So in between is 0. I hope you recognize negative 1 here, positive 1 here. Do I have to check all of them? No. Why not? F double prime is degree 2 and it has 2 answers. So that means really they have to alternate. So I check the 0, and if I put the 0 here, F double prime, put the 0 in F double prime becomes negative 2. Negative, they alternate. And so we say it's concave down here from negative 1 over square root of 3 to 1 over square root of 3. It's concave up everywhere else, meaning from negative infinity to negative 1 over square root of 3 union 1 over square root of 3 to infinity must be concave up. Because of the change, in other words, concave up to concave down, this inflection point, because of the change here, the same thing, we're going to put that into the original function. And because, again, it's an even function, I can evaluate both of them simultaneously. Now, to make sure we understand what's happening, I'm going to do this one first, and I hope you can see that this is 1/3. If this is 1/3, this must be 1/3 to the second power, or 1 over 9, right? So this is 1 over 18. So this is minus 1/3 or minus 6 over 18. So we get minus 5 over 18. And we got our IPs at plus minus 1 over square root of 3 comma minus 5 over 18 precisely. And this is for the sake of graphing, everybody. Plus minus 0.6, negative, let's say 0.3, for the sake of graphing. So I'm going to summarize everything we found, like x-intercepts, max, IPs, minimum, in a table, so it will help me locate everything I need for the graph. Okay, square root of 2 means about 1.4, so negative and positive. So this is negative 1, this is negative 2. So negative 1.4 roughly there, positive roughly here. Okay, we got those. 0, 0, of course, is here. And because it's a maximum, we have a double arrow. IPs. Again, I'm going to go with the approximation. Negative 0.6, negative 0.3. So negative 0.6, negative 0.3 roughly there. And positive 0.6, negative 0.3 roughly there. Negative 1, negative 1/2 is there. And positive 1, negative 1/2 is there. But remember, you need the double arrow for each case because they are also minimum. And we said this is degree even, this is positive. Look, the end behavior looks like y equals x squared, or the first and the second quadrant. So it's this one, goes back up, this one, and going look like that. Check it out. Decreasing, increasing, decreasing, increasing. It's concave up to here, concave down, up to here, concave up. So adding calculus makes it more precise. That's all, everybody. Okay, a quick recap. We have the function. We did the sine graph on f prime of x, gave us minimum, maximum, increasing, decreasing. We did the second derivative, and we did the sine graph on that. It gave us inflection points and intervals of concavity, concave up and down. Now, here's an example that is an application problem. The number of bacteria in millions present in a culture at time t in hours is given as n of t equals 2t times 5 minus t squared plus 14t plus 100. find the initial population. It just means replace the t with 0. When you do that, these two go to 0, so you get a 100 million bacteria. At what time before 10 hours will the population be maximized? First and foremost, let me write this one as 10t minus 2t cubed, and these two add up, and I'm going to put them in descending order. And before 10 means normally from negative infinity to 10, 10 is not included, but because we're talking about time, it's from 0 to 10. 0 is included? Yes. 10 is included? No. Why not? Before 10. I want to remind you of the closed interval theorem that indicates the extreme value theorem or closed interval theorem method. F of x is continuous on closed interval of a to b, find CPs. F prime equals 0 doesn't exist. Find f of a and b, the endpoints and critical points. Absolute max is the largest, absolute minimum is the smallest. We have found n of 0, but we shouldn't and will not find n of 10 because 10 is not included. This is a polynomial of degree. It's continuous from negative to positive infinity, which makes it continuous from 0 to 10 closed, but 10 is not included. That's why we don't. So instead, we're going to find n prime, which is minus 6t squared plus 24, and factor out the negative 6. And minus 6 times t plus 2t minus 2. And when you set it equal to 0, you get two answers. Now you check. Positive 2 is in between? Yes. What about negative? No. You have one critical point. So if you want to go with that, you just basically evaluate at the input and this one and you're done. But I want to show you how the first and second derivatives work. And if it's a closed interval, you don't use that, okay? Because it's half open, I want to use that. So you put t instead of x, you put n prime of t instead of x, and at 2, it's 0. And you do a test point. You can even use 0 and 10. If I plug in 0 into n prime becomes positive and it will alternate. The reason it alternates, it's degree 2 and it has two answers. So, and the arrows increasing, decreasing. So this must be a local max, which becomes an absolute max. If I were to do the second derivative test, first I got to find n double prime. So I'll go back here. N double prime is negative 12t. And then I plug in 2. It either becomes positive or negative. I'm interested in the sign. Negative means looking like this concave down. That means maximum occurs. And so that's why this is easier. Find the maximum population, put the t into either this format or this format. This format seems to be easier because this is 4, 5 minus that is 1, 2 times 2 times 1. This entire thing is 4 plus 14 times 2, 28, and 100 is 132 million. That is the maximum population at the critical point t equals 2. Again, even with half open closed, if you don't do the first and second derivative test is okay. I just want to emphasize how it's done, and it's fairly simple. All right, f of x equals x minus 2 to the power of 2 thirds plus 1. I'm going to sketch the graph, and of course, we want to use the calculus. But what I want to do, I want to remind you how you graph this using transformation and pre-calculus college algebra. First, rewriting this, there are two ways you can rewrite it. Cube root of square root of x minus 2 quantity squared plus 1. Or you could rewrite it in this fashion, everybody. Cube root of x minus 2 quantity squared plus 1. Please understand there are three different ways of representing the same thing. So we're going to start with cube root of x. We are supposed to know all elementary functions, their graphs. And when we know the graph, we know the domain and range is all real numbers, the intercept is at 0, 0. So it gives you a lot of information, and I hope you remember that. Then we're going to apply the -2, which means if x changes to x minus 2, we shift it to the right by 2 units. And therefore, 0, 0 shifts to 2, 0. Now, the next step is to raise it to the power of 2. What happens when a function is raised to the power? Well, the positive side gets larger by that power. The negative side, if the power is even, it flips over, and of course, larger. So the reason it flips over because this is an even exponent. So the location of 2, 0 doesn't change. Finally, we add 1, which means this green one shifts up by 1 unit. And therefore, 2, 0 now has coordinates 2, 1. Very straightforward. In other words, you could see how it's done using pre-calculus. But let's make it precise and go with calculus stuff. So we want to find the first derivative test. Therefore, we are going to differentiate this. To differentiate, we're going to differentiate this one. We get 2/3 x minus 2 to the power of 2/3 minus 1, which is -1/3. The derivative of the inside is 1. You don't have to write it. And you get 2/3 x minus 2 to the power of -1/3. So that's the derivative. We are going to rewrite it by taking this down, making it +1/3, and therefore 2 over 3 cube root of x minus 2. So we have a fraction. A fraction is 0 when the top is 0. It has no solution because the top is a number. It doesn't matter large, small, positive, or negative. F prime doesn't exist or is undefined when the bottom is 0. X must be true. So we do have a critical point, namely 2. So we go with the number line from negative to positive infinity. X goes from negative to positive infinity. And for f prime of x, when we choose 2, it does not, DNE, does not exist. So you want to evaluate this function for numbers to the left and right of 2. So for the left, obviously, as a test point, 1 to the right 3. So let's plug it in. If I put 1 here, I get -1 cube root is -1, and therefore it's negative. In other words, 2 and 3 are both positive. This gives us the sign negative. If I put 3, it's positive, so it's positive. Negative here, positive here, which means, let's throw in the arrows. Arrow down, arrow up. So decreasing from -infinity to 2, increasing from 2 to infinity creates a local minimum at x equals 2. Nothing else, there's no local max. So how do you find the location? You put it back into the original equation. It's easier if you go here. See, if I put the 2 here, goes to 0. Just get 1. So local minimum is 1 at x equals 2, meaning the pair 2, 1. But there's no local max. As mentioned, it's decreasing from -infinity to 2 and increasing from 2 to infinity. Now let's go with the inflection points. If we have any to do so, we have to go with f double prime and set that equal to 0 or doesn't exist. So what is f double prime? Here's f prime. F double prime is 2/3 times negative 1/3 x minus 2 to the power of negative 1/3 minus 1 is minus 4/3. The derivative of the inside is 1. So we get negative 2 over 9 x minus 2 to the power of minus 4/3. X minus 2 to the power of negative 4/3 goes down, becomes positive 4/3, or in this format, cube root of x minus 2 to the power of. Now, we want to do the sign graph, or before we do the sign graph, you may notice 9 is always positive. Okay. X minus 2 cube root of that, positive, negative, it doesn't matter. 4, the exponent is even, is always positive, except when x is 2 and it is undefined. Negative makes this expression always negative. So this expression, because of negative 2, is always negative, except at x equals 2, which means it's always concave down. Do you write it as negative to positive infinity? No. Why not? Because of that. You do write it's concave down from negative infinity to 2 union 2 to infinity. You don't have to use the sign graph. But if you did, f double prime equals 0, x equals 2. See, f double prime equals 0, none. F double prime doesn't exist, 2. And if you do the sign graph, again, same thing, 1 and 3. When you put it here, nothing changes. This negative makes it negative on both sides. You really don't have to do that, because if you notice what I just mentioned, you're fine. So a quick recap. F of x is given, we differentiate. We do the sign graph for the first derivative test to find local extrema and intervals of increasing, decreasing. We differentiate it again, becomes f double prime, and we notice it's always negative unless x is not equal to 2. So it's always concave down. We write it in this fashion. And now we want to graph it. To graph it, I'm going to write, here's the function. Here's where it's increasing and decreasing. Here's when it's concave down, information from the previous page. And you need to find the intercepts, class. And to find the intercepts, if you set x equal to 0 here or here, you get minus 2. Square root is 4, cube root of 4 plus 1. Remember, I showed you the different format. So this is exact, but 2.6 for the sake of graph when we want to do that. X-intercept, we don't have any. Why not? Because x-intercept means set y or f of x equal to 0. So if we set this one equal to 0, this one makes no difference. Then you raise it to the power of 3. First, you move the 1, and then, okay. So you move this. The reason you raise it to the power of 3 first, because the denominator is the index, remember? And so you get x minus 2, quantity squared is negative 1. Something to the power of 2 is negative, doesn't matter what number. No, no solution. Okay, now we are ready to graph this. To graph this, first, let's have a summary table, the points that we have. This one, and of course, means 0, 2.6 roughly, and the minimum is at 2, 1. Let's pick up some points. For example, if I choose x to be 1, I hope you see 1 minus 2 is negative 1. Cube root, negative 1, square it, positive 1 and 1 is 2. If I put 3, I get the same thing because 3 minus 2 is 1. And there are other points. For example, if I put negative 6 with minus 2 is minus 8, cube root is negative 2 square root 4 and 1 is 5. If I put 10, 10 minus 2, 8, cube root is 2 squared 4 and 1 is 5. And I've picked negative 1 on purpose, meaning you have to use a calculator, everybody. Let's plug in. For this one, and this is 5, 10, negative 5, 5. So we're going to start with this one, and I'm going to go with 2.6. So this is 1, 2, 3. So somewhere in between, and that's 2.6, 0, 2.6. 1, 2, 1, and 2. 2, 1, 2, and 1. Now that happened to be a minimum. We write 2, 1 is the minimum. 3, 2, 1, 2, 3, 2. Negative 1, 3.8. So somewhere here. Negative 6, 5. Positive 10, 5. Put them together. Now notice. Decreasing, increasing, right? Minimum. Concave down, concave down. It's concave down everywhere, but not from negative to positive infinity. Rather, negative infinity to 2 union to infinity.